Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Alright, good evening grade 11s. Today we're going to be doing exam questions on electric circuits. Okay, we're going to go all the way back to about 2015, and we're going to run through, or aim to run through, at least up until 2018 today, hopefully in the session. If not, I will follow on with that possibly at a later stage in the year, possibly before term 4 is through. Okay, so I'm just going to get the physical science grade 11 paper open here. Just going to open this in a new tab. Let's have a look at question 10 first, which is electromagnetism, and then we'll move straight on into the electric circuit question, which is just at the bottom, and that'll be the end of the paper. So let's just make it fair. We cover two sections in one. Okay, so question 10, the arrangement of the apparatus to demonstrate Faraday's law of electromagnetic induction is shown below. State Faraday's law of electromagnetic induction in words. Sure, we can all do that. State two ways in which the deflection on the galvanometer, which is this little symbol over here, can be increased. Okay, I have mentioned how we can do that. Then 10.2 goes on to with some calculations, such as calculating the magnetic flux linkage, and then also calculate the number of turns in the coil for 10.2.2, and that's worth 11 marks. Just going to zoom out slightly so we can get all in. And I see it clearly on my screen, so I think we all should see it clearly on our screens as well. Alright, cool. So that'll be question 10, and I'll give about 11 to maybe even 15 minutes for it, and then we'll mark it. Alright, so grade 11, the first question was state Faraday's law in words. Okay, and I'll read it out first before I write it. The EMF induced in a conductor is proportional to the rate at which magnetic field lines are cut by a conductor. Okay. Well, that's one of the ways that we can say it, to be honest. However, the one I like is the magnitude of the induced EMF. And I think this way just sounds a little bit more professional. Alright, in a conductor is equal to the rate of change. I was going to say in, but it's actually of the magnetic flux. Or you can go a step further and say of the magnetic flux linkage. Okay. Cool. The next question, let's go check it out, was state two ways in which the deflection of a galvanometer can be increased. Okay, well, one that's very obvious for me to remember was to move the magnet quickly or quicker, or you can say quickly or quicker inside the coil. One of my ones that I used to always say in the exam, and use a stronger magnet. So I'd alternate which one I want to say first. Okay. Hope we all got that one. Or those two. Pretty basic, pretty simple. Okay, all have enough space? No, I won't, so that's the end of that one. Okay, cool. I'll leave you all to take that down for a few seconds. Now 10.2.1 says a coil with an area of 0.6 meters squared is held with its axis coinciding with the direction of a magnetic field of strength 0.4 Tesla. So now they've told you the angle of theta in that two line little text there. They said the coil with an area of specified there held with its axis coinciding with the direction of the magnetic field. So in other words, its axis line is pointing in the same direction as the magnetic field lines. So it means there's no angle formed. Okay, so they've told us the value of the area, which is A, 0.6 meters squared. The value of B, which is the magnetic field strength, 0.4 Tesla. Angle theta is equal to 0 because the lines are like this. They are parallel with each other. Okay, I can take that out. Theta is 0, and we asked to calculate what is the magnetic flux. So we take the formula. Magnetic flux is equal to BA cos of theta, 0.4 multiplied by 0.6 cos of 0 degrees, that's 1. So it's just 0.4 times 0.6. Therefore, magnetic flux here is equal to 0.24. We can say Tesla per meter square, or WB for Webers or Webers, whichever one. I just say Webers. Okay. Alrighty. Awesome. Moving on to the next question. In order to produce an EMF of 9 volts, the area of the coil with its axis coinciding, there's that word coinciding again, with the direction of a magnetic field is halved from 0.6 to 0.3 meters squared in 2 minutes. Calculate the number of turns in the coil. Alright, completely different question now. Okay, however, not too difficult. Alright, can be done. Okay, with ease. Okay, first things first, we've got a new area. Okay, so that means we're going to have a new magnetic flux. If the area was halved here in the first one, okay, 0.6 meters squared to 0.3 meters squared, okay, then we're going to have an instance where we're going to have the same magnetic flux, so 0.4 times 0.3 times cos 0, and we're going to get 0.12. So basically, the magnetic flux is halved, since the magnetic flux is directly proportional to area as well. Okay, so we can say that half the magnetic flux is going to equal to 0.12 Webers squared. If you want the calculation for that, okay, that's basically saying phi is equal to the same formula here, which is 0.4 multiplied by 0.3 cos 0 basically equals 0.12 Webers. Okay, I just used a bit of logic. Cool. I will just erase this so I can have space to work, because it's going to be quite a big calculation. Okay, cool. So now we use the formula negative n. Sorry, not negative n. Should be EMF rather is equal to negative n times the change in the magnetic flux linkage, all divided by change in time. Okay. Just checking for the arrival of another student. Cool. Hasn't arrived yet. Okay, so they've given us an EMF. Okay. We've now got 2 values for the magnetic flux. Okay. So this was it initially. This was what it ends up being. So we come up here. I'm just going to halve the screen here so we can work with the other side here. So we've got 9 volts is equal to the negative n, which we have no idea what it is. Remember what the negative represents, so we don't bother too much about it. We've got 0.12 minus 0.24, and then divided by 2 minutes, which is 120 seconds. Okay, and 9 is on the other side. So let me not be a chop. Let me actually move this away. Cool, got that. So this will be negative 0.12, because 0.12 minus 0.24, add that in there, which gives me negative 0.12. 9 times 120, Foolish of me, I do not have my calculator open, so let's get it open here. 9 times 120 gives me 1080, so I've got 1080 over here is equal to negative n times negative 12. I just have 0.12 n. It's divided by 0.12. And if I do that, I'll get the number of turns, which is n is equal to 9,000 turns. Alright, we're going to move on to question 11. Question 11 is now the circuit question. It says, the circuit below is used to determine the resistance of resistor X. Okay, they say a 12-volt battery, which we see labeled there for us, has negligible internal resistance. When switch is closed, the reading on the ammeter is 0.5 amps. Want us to state Ohm's law in words and then calculate the resistance of resistor X. Okay, so let's do 11.1 first, and I'll give roughly about 7 minutes for it. 2 questions, and then we'll come and mark 11.1 before we move on to 11.2, because all the questions are sitting nicely underneath the circuit. Okay, question 11.1 of the same paper, 11.1.1 asks for Ohm's law in words. Alright, and that would basically be that the potential difference, which is the voltage though, but we have to say potential difference across a conductor is directly proportional big words here, directly proportional to the current in the conductor, provided that temperature remains constant. You can say remains, I'm just going to say is constant. Okay, which is the most important part there, or one of the most important parts. In fact, every part is important there. The temperature must be constant. Okay. 11.1.2, I do believe, was the calculate the resistance of resistor X. Okay, so the total voltage, total potential difference, or EMF, whichever you wanted to call it, was 12 volts. The current in the ammeter was 0.5 amps, and the let's see here, one resistor was 8 ohms, so I'm just going to call resistor 1 8 ohms. Okay, so what we could use is the same formula that we use here in the definition, is that V total is equal to total current times total resistance. Okay, so with V we got here was 12, so I'm going to come a little bit over here. So 12 is equal to 0.5 times R total. And that's the total resistance in the circuit, which we're also not sure about. So if we divide both sides by 0.5, we'll get that the total resistance that should be in the circuit should be 24 ohms. It's the total, tot for total. Alright, now we asked about resistor X, but we were told that one of the resistors was 8 ohms. So if we come here and we say, well, the total resistance must be the sum of R1 plus R plus X, or Rx, right? So we have 24 is equal to 8 plus Rx, which would be, in order to find out Rx, it would be 24 minus 8. So therefore, resistor that is named X, 24 minus 8 should give me 16 ohms. And that is the end of 11.1.2. Alright, 11.2 is more of a major circuit here, or bigger circuit. We've got parallel components there and everything. Study the circuit below. The battery has an EMF of 12 volts with negligible resistance internally. They say now that switch S is closed. Write down the potential difference across the 4 ohm resistor. That was 1 mark, so that means the answer is on the circuit. 11.2. Calculate the reading on the ammeter, 5 marks. And 11.2.3 is calculate the energy dissipated in the 12 ohm resistor in 2 minutes. Okay, that is a power formula. Okay, so 11.2, 5, 10, 11. So I'm going to give about 12 minutes for it. Let's go. So 11.2.1, let's start the first question here. Write down the potential difference across the 4 ohm resistor. It's 1 mark. So the 4 ohm resistor is sitting nicely in a parallel branch right here, opposite the battery. Okay. If this was a voltmeter reading here, it would be parallel, would be up across the 4 ohm resistor. So the 4 ohm resistor will have a potential difference of the battery. The EMF, it'll be 12 volts. Okay, so let's just scrap this one, get the other layer here. 11.2.1, it'll just be 12 volts, because as you can see, the battery across it looks exactly as if a voltmeter was opposite it. It's the same thing. Literally, the voltmeter would have read 12 volts. The battery is 12 opposite the 4 ohm resistor in a parallel branch. They are the same value. Okay, parallel branch. The voltage across each resistor will be the same. In this case, it will all be 12. Now, the next question is 11.2.2. Calculate the reading on the ammeter. Okay, so how are we going to approach this question? Okay, so we can approach it quite a number of ways, but I'm going to do the one I think makes the most sense. Okay, we're going to take what is the voltage going across the 4 ohm resistor, and let's find out the let's try and find out the current going through the 4 ohm resistor. Okay, and let's take the resistance of the 4 ohm. Okay, so we'll have 12 because that's the voltage going across it. It's 12, and if I is unknown, times by 4. Okay. We rearrange, or we divide both sides by 4. We'll have the current going through the 4 ohm resistor to be 3 amps. Okay, got that. Now, opposite to the 4 ohm resistor is also the 16 ohm resistor, because they are in parallel with each other. And the parallel voltage is the same across both resistors, so it's 12 volts is also the voltmeter reading on the 16 ohm resistor. Okay. Things are all taught last week. So, voltage to the 16 ohm. Okay. Same formula. 16 R 16 ohm. We just specify these little subscripts to help us realize, okay, which or what we are working with rather. So it's still 12. That's still current. That's times 16. And if we divide both sides by 16, let me check. I think my maths in my head is correct. Yeah, that's 3 over 4. So that would be, the current over here would be equal to 0.75, which is 3 over 4 amps. So then the current on the ammeter would obviously be the sum of these two together. 3 plus 0.75, which would equal, therefore, to 3.75 amps. Why does this make sense? Number of reasons. 1, current, look where the ammeter is situated. Current splits in a parallel branch. We have everything that we need because we have the resistance values of both resistors and the volt or potential difference across both, because it's a parallel branch. So we can easily calculate the current going through each of them respectively and add them together, because current splits in a parallel circuit or in a parallel branch, meaning that it must split and rejoin. So when it splits, it can only split of the total current. Only the total current can split. In which case, 3,75 split it across the 4 and 16 ohm resistor into 3 and 0,75 respectively. Okay, so 11.2.2, final answer there for the current that's reading on the ammeter is 3,75 amps. Okay, let's finish and then I'll answer any discrepancies. Let's come over here. Okay, 11.2.3. Okay, this is slightly different. I think they're asking for the energy dissipated in the 12 ohm resistor in 2 minutes. Okay, so the resistor that we're busy with here is 12 ohm resistor, and the time here is 120 seconds because it's in 2 minutes. So just make sure. Okay, so what we need to do here is there's a number of ways that we can do this. Okay, let me see what is my favorite one. This formula that goes by the voltage going across the 12 ohm resistor is equal to the resistance of the 12 ohm resistor, which is going to be 12, divided by the total voltage, or total resistance rather, R total, multiplied by the total voltage. Okay, if you didn't know that formula, now you know, because we need to get the voltage going through the 12 ohm resistor. What we do know here is we got 12 plus 8. Okay, so all we are looking for is this part over here. Okay, that's all we're looking for. Okay, we're not really looking for anything else because we're looking for just that part here. So we're going to use 12 plus 8. We can use another formula, but the formula that I'm thinking of is a formula that we only really bring into grade 12. Okay, only really bring that into grade 12. You know what? This is what I'm thinking. I'm actually going to do it this way. Sorry, guys. Let me just, I just had a brain fart. I'll show this another time. I'll show that another time. I just had a brain fart quickly. Let's calculate the parallel resistance first. Okay, so R parallel, you've got, of course, R1, R2, all divided by R1 plus R2. Okay, which in this case, you got 16 times 4, all over 16 plus 4, which is 20. Okay, and what that's going to do is that's going to give you a formula of, let's see, sorry, not formula, answer of 3,2 ohms. Okay, now you got to be careful here. It's because these two parallel resistors are in parallel to these. So you got a parallel branch and a small parallel branch. So you got 2 in 1. Okay, so you need to watch out for this. Okay, now you need to take R parallel again. Okay, which is basically the 3,2 ohms multiplied by 20. Where's 20 coming in? Because they are in series with each other, they are counted as 1. So that 12 plus 8 equals 20 over 3,2 plus 20. Okay, so this was of 1 and this is 2. So now your final parallel branch, or your total resistance now, is going to equal to, let's just put this in a calculator, 3.2 times 20 over 20 plus 3.2. That gives us an answer of roughly 2,758 ohms, round up to 3 decimal places. Now I'm going to switch colors quickly and say, well, the total voltage here must be equal to the total current times the total resistance. Total voltage here, we know, is 12 from the EMF. The current is unknown, times 2,758, which is our total resistance. Therefore, simple maths, get rid of the 2,758 so we can have current on its own. The total current in the circuit will be 4,351 amps. Okay, that's great. So now, if we want to know what is the current going through the 12 ohm resistor, because current is the same at any point in the circuit, in a series circuit, current is the same. Alright, the same current will pass through the 8 ohm resistor that will pass through the 12 ohm resistor. The same current will do that. Okay, so what do? Is we say that the current that's going through the 12 ohm resistor is going to equal the total current, which is 4,351, minus the current that is going through the parallel circuit, okay, which is 3,75 that we calculated earlier, okay, and that'll give us 0,601 amps. Okay, so that is the current going through the 12 ohm resistor on top. Now what we do now is we say, well, we find the formula with energy that has current in it. It's got I squared R times delta T. Okay, and obviously there's another formula as well using voltage, but we're not going to use it. So the current is 0,601 squared, okay, times the 12 ohm resistor times 120, which was 2 seconds. If we add that in on our calculator and we multiply it all out, we'll get an answer of roughly, let me just do it quickly, 0,601 all squared multiplied by 12 multiplied by 120 will give us 520,13 joules. Okay, and that is one way, of course, to do it. There is, however, there is another way. Okay, there is another way. That's a bit quicker, and I would like to demonstrate it quickly, actually. If I take, what's the voltage going through the 8 and the 12 ohm resistor? Okay, voltage going through the 8 and 12 is equal to the current times the resistor, or the resistance of R8 plus R12. In other words, the 12 ohm and the 8 ohm resistor. Okay, so voltage again is 12, and we've got current, which is unknown, going through that sector. 12 plus 8 is obviously 20. Okay, divide both sides by 20, and therefore current will equal 0,6 amps. Very similar to 0,601. Okay, 0,6 amps. So now the voltage that's going through the 12 ohm resistor would be equal to I times R. Okay, the current going through the 12 ohm resistor, which is 0,6, because the same current goes through resistors in a series, the same current, doesn't matter, doesn't split like with a parallel circuit. 0,6 times by 12 gives me a total voltage of 7,2 volts. Now the energy dissipated would be W is equal to V times I times delta T, which is another formula for energy, which will equal 7,2 times 0,6 times 120, because we have to factor time in. And then that'll give us answer that's slightly different to this answer because we use rounded up answers here. This will give us an answer within the same range. The range is from about 518 to about 520 odd. So 518,4 joules would still be right if we use this formula, because there is a range of answers for the decimals. There's a range. Okay. Like, there is another way to do it. There's more than one option. Okay, there's more than one option, but we're not really going to go through that at this point in time. Okay, these two options I think were about the easiest. This one was a bit longer, calculating the two parallel circuits, or all the resistors in parallel with each other. Okay, going through this question over here, we can see these two are in parallel with each other, but this whole branch is in parallel to both of these, but they are in series, so you can count them as one whole resistor almost. So the first method could have gotten a little bit tricky if you didn't follow along. But I had to showcase it in any case, in case one of you did it that way. But the second option here that I showed you, a little bit quicker, a little bit easier. You just had to use this version of the energy formula. Okay. Thank you, grade 11s, for joining me this evening for circuits, electromagnetism and circuits. Next week we'll do some more past papers to make sure that we have this section down, as this section only comes naturally with tons and tons of practice. So next week we will run through another 2 questions section of electricity and magnetism in another past paper.